Other than that, do you guys have any question?
So we can call it any other component like 3x NAND or like 3F NAND. Okay.
Yeah.
Professor, I just have a question about the homework.
Sure.
Can I share my screen? Is that possible?
Which part?
Just
Share your screen.
Yeah, sure. So for the logic-based stuff, when I'm actually like kind of looking at the path that is supposed to be kind of like, because this is what I drew for the first one with the NAND gates.
Okay, this is the more, yeah?
Yeah, so would this be technically a critical path of 4? Because it has to move through, so for like one input, it has to move through this node, and then these nodes? Or would it be a critical path?
The longest one, it will be 1, 2, 3, right?
1, 2. Oh, yes, I do, because that's just a complete
longest, right?
signal. Got it. Okay. I was just kind of wondering about how to calculate that. So. Okay, sounds good. Thank you.
Okay, now let me just share my screen. Any question before I start regarding the homework? There is no question?
I think I had one, just like trying to determine the critical path. That was like a little bit confusing for me, like just to how to determine it.
What's confusing you? Which part?
Like how to I guess you would say like determining the critical path. Like I know you're supposed to be like find like the longest route.
It's gonna be the longest between the input and output. How many gates in that path, right? Do you want me to make an example?
Yes, please.
Okay. Anyway, so now let's say that we are looking for now we're gonna build a circuit, okay? So this circuit is gonna be used what? Gate level implementation. What we are doing now is called gate level implementation. Okay. Today is what, 22nd? Okay. Anyway, we're gonna build everything using what? Just leave normal gates because we don't want to waste time then. Okay, so what is the subject here? We need to build something that's called full adder. What is this full adder? Full adder, normally it has input, and carry, and input and output. What is this? So if you like to add A to B, I'm adding A to B, okay? The output will be sum here. Sounds good? But then, there is another one, it's called C. So that means I'm adding A to B to C. And I'm expecting this output will come to what? To a carry out. Do you agree? Because it's a binary system. So we are expecting any carry out to come, right? And I call this carry out. Later on, I will describe to you what is this, but just focus on this. This is a single bit. Single bit, that means 1 digit. Single bit. And then the output here is going to be single bit and single bit also for the carry out. Let's admit it. So, and this is add. What should we do as a designer? First of all, I go to what? I go where? I go to the truth table. So I have truth table. Number 1, create truth table. Okay, truth table look like this: A, B, C. Those are the 3 inputs I have. Do you guys agree? I have 2 outputs: sum, carry out. How many states this table is covering?
9.
Why 9?
Oh, sorry, 8.
Yeah. Why 8?
Because there's 3 inputs.
Okay, and then if 3, then what happened?
You multiply by 2 because there's only two states. Sorry, it's power of 2.
No, it's not power of 2.
2 to the power of 3.
Oh, sorry, 2 to the power of 3.
Yeah. Power of 3, exactly. Thank you.
Yeah.
So now it should be 8. 1, 2, 3, 4, 5, 6, 7, 8, right? And we know min terms, max terms. You guys agree? So this is M0, M1, M2, M3, M4, M5, M6, M7, right? And this is 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. Make sense? Now we are applying adding. So every single state will be added to each other, right? So now this one added to this one, added to this one. The output will be what? 0 added to 0, added to 0. What the output will be?
0.
0.
0. And I don't have any carry out, right? Here, 0 is added to 1. What the output will be?
1.
Is there any carry out?
No.
Yes.
Yes. Why?
I thought C was a carryout.
Really? So 0 plus 0 is what? 0. 0 plus 1 is what? 1. Is there any carry out? You know what's carry out mean, right? So carry out, you know, if 0 plus 0, what is the output of this will be? Huh? Andrew?
0.
0. Is there any carry out of this?
No.
Okay, so 0. Now, if 1 plus 0, what the output will be?
1.
1. Is there any carry out?
No.
Okay. If 0 plus 1, what the output will be?
1.
1. Is there any carry out?
No.
Okay. If 1 plus 1, what the output will be?
0.
0. Is there any carry out?
Yes.
Okay. So this is basically what I'm using now to do this. Okay. So 0 plus 1 is 1, and there is no carry out. That 1 added to 0, it will be what? 1. And I don't have any carry out. Now, 0 plus 1 is 1. That 1 added to 1 is what?
0.
0, and I have carry out. Same thing here. So going to be here 1, 0. Here going to be 0, 1. There. M6. 1 plus 1 is what?
0.
0. And is there any carry out?
Yes.
Yep.
Yes. Then you know 1 plus 1 is what? 0. You added 1 there, it will be 1, and there's carry out. That makes sense?
Yes.
So for the M7,
Uh-huh.
it's so the one that carry out from A and B that still falls on C. Like it's 1 plus 1 plus 1.
Look at this. Look at this. 1 plus 1 plus 1. You agree? So
Yes.
1 plus 1 is 0, right? And I have carry out, right? So put
Right.
carry out here and I have 0 in my hand now, right? That 0 added to 1 to be what?
1.
1. And the carry out is still here, right?
Oh, okay.
That makes sense?
Yeah.
9 plus 6, you remember in the decimal is what? 15, right? 5, and the carry out went here to be 1. So that's why it's 15, right? Same thing. Okay, anyway, I don't want to waste time in this, but anyway, now we have two functions, right? Function is called sum, and the variables input ABC, and the function is called carry out, and the variables are A and B and C. That makes sense?
Yep.
Okay, so just building any circuit of any circuit, you know, with all of this optimization thing, I can just write here the function after optimization, because you know the question is not answering optimization. So here sum is equivalent to A XOR B XOR C, period. Okay, carry out is an A ended with B, ORed with A, ended with C, ORed with B, ended with C. This is after optimization. Okay? Sounds good? Implement. Show me what's gonna be the implementation. So you already have in here A, with B and XORed, right? The output will be XORed with C. A, B, C. That will be carry out. Make sense? Hello? Hello?
Yes.
Okay. Now,
Sorry, wouldn't that be the sum?
huh? Sorry, gonna be the sum, yes. Now,
Yeah,
we're gonna
nice.
go to the carry out, right? So A ended with B. Do you agree? Then you know A ended with C. Those together are what? ORed. Do you agree? So here is an OR. Then that thing here is gonna be ORed with product of this, right? So B and C were, so here is B, here is C, and those are AND. And the output here will be ORed. So here is official output. Do you agree? So this circuit has 3 inputs and 2 outputs, right? I need to know what is the speed this circuit should actually follow, right? What is the time window that the output will come correct? So what does XOR how to look like, right? XOR, if I'm using NAND gate, right? NAND gate to implement everything, right? If you are implementing XOR using NAND gates, how many gates the longest pass will be? Somebody tell me. Do you guys remember?
What was the question again?
I think it was 3.
It was 3 in the longest, right? So XOR is equivalent to 3 T NAND, right? And is what? 2 NAND, right? Because it's NAND followed by inverter. So gonna be here 2 T NAND. Or it will be what? Do you guys remember? Huh? Or using NAND. Do you remember how it looked like?
Wasn't it 2 as well?
Right? X, Y, X complement, Y complement. Here we're gonna be what? X complement, Y complement, complement. So if you do it, it's gonna be X or Y, right? So in that case, the longest is this one. It's gonna be 2 T NAND. Make sense? Now I'm gonna put these values on the figures in front of you. So here I have 3 T, 3 T, 2 T, 2 T, 2 T, 2 T, 2 T, right? What is the longest? There is a pass here between the input and output, which is 60. There was another one also, which is 60 as well. Then there was another one, which is from here, going to there, going to there. This is also 2 plus 2 plus 2. So gonna be 60, right? There's another pass, which is basically from here, going to there, going to there, going to there. Also 60. And then, there's another pass, which is basically from here, going to there, going to there. And same thing for the second in period, this one. That's 60, right? And then, the last one, there is a pass from here to there. And that's actually 2 plus 2 gonna be 40. And then, there was another one, which is gonna be also 4. So the shortest is 4, the longest is 6. That makes sense?
Yeah, so it will be 60 then.
Yes, so this circuit has to run in 60 NAND. And 16 NAND, let's say, is maybe 4 nanosecond. So this circuit, it will form, if I give the input, the output will come after what? 6 times 4, so that means 24 nanosecond. Any question?
Professor,
Yes.
how did you derive the formula for Cout? 'Cause I didn't.
You mean this?
Yes. How did
I
you?
optimized. You know, the question, it was about the critical path. So that's why, you know, I didn't make the optimization in front of you. I just optimized it.
Oh, you optimize the A.
After optimization, yes.
Okay.
Okay, look. Any question?
Oh, how do we get the values for each gate? Like how you have 3T and then 2T?
Do you remember the last lecture?
So I just watch the replay on that.
Yes.
Okay.
Because, you know, that showed how the XO was built from NAND gate, right? How the AND gates used, you know, for instance, I will make one example in front of you. I already made the X here, the OR, right?
Oh, you use, oh, never mind. I got it. My bad.
Yeah, so the AND, the same thing. Look, what is AND? Here, AND is basically NAND, right? AB. It's going to be AB complement. Then it's AB complement, which is AB. So what is the longest path? Both of them too, right?
Right.
Okay, anyway, any other questions before we move to the next chapter?
Yeah, can you scroll up a little bit?
Sure. Okay, any other question? Hello?
I'm just trying to figure out how you got the function so quickly.
Which one? You mean this one?
The sum and the sum and the CL. How did you derive the function so quickly from the truth table? It's just practice.
It's not practice, you know, I'm a designer.
Oh, yeah, you have all the, yeah, I guess you've been doing it for a while.
It is my job. Right? So, you know, I have a bunch of US patents for this. Okay.
Yeah. So is that something that we should be like coming up with like right away like that?
Yeah,
too?
I mean, after the course will be done, you should be like that immediately.
Okay.
Okay, that's why I'm gonna give you the K-map. And then we're gonna do the same example again with K-map. And then I will show you, if we do this using the postulate, it will take time. So
yeah, definitely.
I will tell you why. So the postulate is great, right? But it's great in a certain level. Because do you remember when, like, sometime when I was trying to do derivation in front of you and we just like reached a dead end, and then, you know, we came into the point, oh, we have to look at it again, and then we'll do it one more time. So, because, you know, sometimes, you know, we are, you know, our brain, end of the day, is limited. It's not parallel.
Definitely.
It's processing some stuff sequential sometimes, you know? That's why, you know, the mathematician moved to the K-map. And the K-map is going to be our topic today.
Oh, cool. Okay, I don't know what K-map is.
We'll do the K-map, then I will do the same example, exactly this same example, then, you know, I will show you how it's really easy.
Okay, cool.
Professor,
Yes.
just to make sure, I know I asked that before, but like the equation or the function you optimize, was it the A exclusive or B, and like, is it the equation above the sum that you optimize for it to be A dot B and all that?
Okay. My question to you, what is the equation without this optimization will be? It will be for sum equivalent to M1 ORed with M2 ORed with M4 ORed with M7. Do you agree?
Yes.
Those after optimization would be like that. Sounds good? For the carryout, you have M3, M5, M6, M7 will cause this.
Okay. Okay.
Okay?
Yes.
But we'll learn it through K-map now.
No. You can do it with the postulates, but you know, You know, let's be systematic here, right?
Okay, okay, okay,
The topic of the lecture is K-man.
okay.
But then, you know, you can do it with postulates.
Okay,
That makes sense?
yeah,
So if you want, you can take it as a homework. Try
sounds
it
good.
here, homework. Do it with postulate, please. And then, you know, if you're stuck in it, then, you know, we can discuss it.
Sounds good.
Sounds good?
Yeah.
And you know that you, Wednesday, this coming Wednesday.
Thank you, sir.
Okay, so again, so to be clear, this is what a circuit is used for adding 3 different inputs, A and B and C, generating outputs, sum and carry out. The table is actually covering the relation between the input and output truth table are covering 8 states based on the little itty bitty info we know. 0 plus 0 is getting 0, carry out 0. 1 plus 0 is 1, carry out 0. 0 plus 1 is 1, carry out 0. The only state will cause me to have carry out when both of them are 1. That means they reach the ceiling of the digit. The ceiling of our digit is 1. The bottom of our digit is 0. Do you agree? Then, based on this fact, we filled up this table, right? What I show you the optimized equation describing the relation between an input and output. The reason, because, you know, we were covering what the critical path. But if you're willing to do the optimization using the traditional postulates or the Boolean algebra we learned in chapter 2, I give you homework due on Wednesday to give me the sum and carry out exactly look like that from the postulate. What we're gonna do now, we're gonna do it using K-map. Sounds good?
Yep.
Okay, now chapter 3, K-map, gate level optimization. So K-map, it's a great mathematical solution for optimizing Boolean algebra. But there are forms of it. So K-map, we can find 2 input, 2K var, 3K var, 4K var. What does it mean? It covers 2 variables, 3 variables, 4 variables. But, you know, somebody can tell me, what about 5 variables, 6 variables? It will be a mess. So the most manual way, as you know, by hand to do, it's 2, 3, 4. 5, 6, 7, there is a trick so you can break up to multi-4s and multi-3. So what is actually 4? 2 variables. So my question to you, how many states do we have if we have 2 variables input?
4.
4, exactly. So now our topic is a 2 var K map. So I'm expecting this map to have 4 elements, right? 4 states. And those are the 4 states. And you have here the line which is breaking between who is in a vertical, who is in a horizontal. So imagine that, you know, this 2 var, they called A and B. So I have the variable called A and B. So I have A here and B there. A, from your point of view as a variable, is holding 2 values, 0 and 1. Do you agree? So 0 and 1. B also can be what? 0 and 1. Do you guys agree?
Yep.
Now you're gonna see something. K-map is not inventing something new. K-map is just taking the truth table and reordering it in a graphical way. So A 0, B is 0. This is M what?
M0.
M0. A0 B is 1. This is M what? M1. And A1, B0, this is M2. And A1, B1, this is M3. Based on what? If you write your table A, B like that. Do you guys agree?
Yes, that makes
Yep.
sense.
Okay. So if I like to describe in a variable syntax, this is when B is 1, so that means B. When I see this is 0, that's actually the B complement, right? Same thing. This is the A complement, and this is what? A. Right? Let's have some example and see how we're gonna deal with. Okay. So imagine that K map came to me to be 0, 1, 1, 0. And this is X, this is Y, 0, 0, 1, 0, 1. So the mathematician who built the trick, he came into a point saying that, we are seeking the number of ones, which can be 2 power something. We are grouping them. They have to be neighbors so we can group them. Since, this is horizontal, vertical, so who is neighbors we can actually group from your point of view. So, I can group 2 power 0. I can group 2 power 1, 2 power 2, up to. This table can be grouped as follow. I can group, for instance, those 2 guys together. How many ones in this group? 2, 2 power 0. Do you guys agree?
So do we start from 2 power 0?
Yeah, I mean 2 power 0, 2 power 1. So basically,
Okay.
you are looking for 2 ones nearby, 4 ones nearby, 8, 16, and move forward. You know what I mean? This table, maximum you can have, that means the whole table are 4, right? So this table can be 2 power 0, 2 power 1. That makes sense?
Yes.
Okay. So now I have these 2 guys together. Do you guys agree? So these 2 guys together, horizontal or vertical? They are vertical. Okay. So while I'm looking to the ones and I group them, I call this group 1. Is there any other group I can group from your point of view?
Group 2?
I don't have any group. The only group I just have group 1.
How about the zeros?
Those zeros, I cannot group them. I group the ones.
Oh, just the ones.
Okay. So in that case, I can write function of X and Y is equivalent whatever in group 1, which is, then I start looking horizontal and vertical. Horizontal and vertical. So how can I do this? Now I'm looking into the horizontal. So what I found in the in the vertical, what I found in the vertical, Y equivalent to 1. Do you agree? In that case, I can write here Y. Then I end the horizontal with the vertical. So now it's a term for getting the horizontal feedback. So in horizontal, I go with this color. So basically, here's the 2 horizontal I have, right? Where's the 1? I have 0 and I have 1. Do you agree? Those are the only 2 things I have, right? So pretty much I can write here, it's gonna be X complement or with X normal. So I can literally come and say, this function, if this happened and that happened, then it's actually representing Y. More practice, you'll figure it out. Okay? Let's look at it as a postulate. You already have here M0, you have M1, you have M2, you have M3. Do you agree? This function is M1 ORed with M3. Do you guys agree? Hello?
Yes.
Yes.
So which means that M1 is what? Huh? M1 is what? X complement Y ORed with X, Y, right? If I take it like this, I will take Y as a common, gonna be X complement X, so it's actually Y. So this value is equivalent to this value. So with postulate Y, with visualizing, it came Y. So far so good? Now, if I make a different combination inside the two var, so here is the two var, right? I have here X and I have Y 0, 1, 0, 1, and here is M0, M1, M2, M3. And what I'm gonna write, I'm gonna write here 1 and I'm gonna write here 1. Somebody will come and say, Professor Ali came and say, this, we are grouping ones. So I can just go like this and take them. No, you are just allowed to group in a horizontal vertical. You cannot grouping in what diagonal. So in that case, this is not the case. So the only one I can think about in my head, I can consider the 2 power 0. 2 power 0 is 1. So that means, I just group this as a group and I group this as another group. So now I have two groups. So in that case, I can write fxy is equivalent to group 1 ORed with group 2. Sounds good? So this is 0, 0. So I can write it in a literal. So basically, oh, scheiße, sorry. I can write it as a literal. So in that case, group 1, I will go horizontal and vertical. Okay, I'll do it one more time and then you guys can go ahead with me. So in this group, I'm looking what? Vertical. I'm looking vertical, right? This vertical is pointing to what? Y. Do you guys agree? So here we're going to be what? Y. Then I will do the horizontal of it. So the horizontal of it is actually pointing to X is what? Complement. So here is basically X complement. Then I go and OR, and I look to the second group. Second group, horizontal, is pointing to Y complement. So going to be here Y complement. And I go vertical, I go horizontal. So this X is actually X. So going to be here X. So pretty much this K-map is representing the formulation of what? X ORing between X and Y. So in that case, I can write, is X ORing between X and Y. Make sense?
Is it always plus for the
Yeah, I mean,
Group
you
one
four
plus group two.
groups and you end because it has min terms. Do you agree? Do you agree?
okay.
It has min terms. In the min terms, do you remember the min terms? Do you remember the trick of the min terms and POS and SOP and all of this you will discuss on max terms? This table, this K-map is representing the truth table. And the truth table, how it works as an output, you start ORing min terms, right? We are doing the same thing. So far we already have a scenario, 2 of them there. Another scenario, they are going diagonal. Let's go to another scenario, which is basically you already have a function like this. Here is an X and Y, 0, 1, 0, 1. And then, here is, I write, like when I write like this, that means I'm talking about the M. So learn it from me like that. This side, I make it like min M instead of writing M0, M1. So what about if I make it like this? 1, 1, 1, 0. Now I look into the maximum I can group. So the maximum I can group, whether they're going to be horizontal, vertical, is basically 2 power 1. Why? That can be a group. And I call this group 1. Somebody will come and say, and this is group 2, because, I didn't group it. Nope. You are allowed to group in something grouped to make more optimization, less resources to be used. So in that case, I can just go ahead and group like that. And that's going to be my group 2. Is there anyone it's not written in the groups? Is there anyone in the map now in front of you not involved in any group? Of course not. Because those two guys in this group, those two guys in this group, and this 0, I don't care about it. So I'm done grouping. Now I will start analyze the group into what literals. So in this case, I can write F, X, Y equivalent, and I will take group what? I write group 1, ORed with group 2. So let's do it. So in that case, I can just go ahead and take the color like this, and I say group 1. So group 1, you know, vertical, I'm talking about, you know, Y. Ended with the horizontal of it. Horizontal, it's coming into like this. Why? Because, you know, I have one here and I have one there. So basically, you know, in two rows of the horizontal, right? So in that case, it's gonna be ended with X complement X. Then, you know, I go in a group 2. Where is group 2? Group 2, this one. So I use a different color here, and I'm looking for the horizontal vertical, right? So basically the horizontal of it is this one. So it's gonna be X complement. Then ended with the Y vertical. So my Y vertical in this case is what? This and that, right? So gonna be what? It's gonna be Y ORed with Y complement. So if I start using my postulate of X complement ORed with X, this is 1. This is 1, so I can write it as Y ORed with X complement. This is the final optimization. You cannot do optimization more than that. Any questions so far? Any question?
Just trying to wrap my head around it first. Sorry.
No, that's fine. You know, that's why we are learning, right? Now, there is another possibilities in this table, and then, you know, I will give you a very nice quick thing, which is basically going to make it even much better. We talked about one element by itself. We talked about, you know, 2 elements in a horizontal or vertical, or 3 of them, and we group. So what is the ultimate we can have is actually the whole table are ones, right? So basically, you know, ones like this. So, you know, location 0, location 1, location 2, location 3, X, Y, 0, 1, 0, 1, and here is 1, 1, 1, 1. In that case, I look into the 2 power what? 2. Why? Because literally those guys are neighbors. So I can actually group all of them in one group, and I call it group 1. So F as a function of X and Y is equivalent to group 1. And in that case, let's go into group 1. So group 1 horizontal is going to be this direction. So going to be X complement ORed with X. And then, you know, you're going to end it with the vertical. So the vertical of it is going to be what? It's going to be Y complement and Y. So going to be here Y complement Y. So pretty much is equivalent to 1, ended with 1, which is 1. Something we can actually notice, and I will do it again in front of you. So in the case of the first case of X and Y 0, 1, 0, 1, right? When I made 1, 1 here, right? At end of the day, the horizontal remove each other. Do you guys agree? So here is 0 and 0. So when I group like this, when I looked horizontally, I actually take X complement and X. So I can actually claim, if I look to such a kind of problem, I don't need to do this intermediate trick. I can just come and say fxy is equivalent to just the only vertical, and in this case is heading into y, so it's equal to y. That makes sense?
Yes.
Same thing. If I do a table like this, and I write here 1, 1, 1. And I go here 0, x, y. So end of the day, I have two groups. Do you guys agree? So this is group 1 and this is group 2. So basically, that's actually group 1 ordered with group 2 is equivalent to what? Let's go ahead. So group 1, the only thing I need to think about is the vertical. Because identifying it, it's actually just belong to y. Because, you know, here's 0 and 1. It's going to be y. Then if I look into the group, the second group, group 2, this is actually naturally what horizontal. So basically, you know, this is actually donated into 0, 1. So basically, I'm looking into the only thing here is y x complement. I'm sorry, x complement as an output without even looking into the vertical behavior, because, you know, they're going to remove each other. Make sense?
So if that one on the top left was on the bottom left, it'd be y plus x.
Yeah, we can try. Let's do this. You know, x, y, 1, 1, 1, 0. What do you think, right? Let's do it. So how many groups I have here? Now I would like you guys to interact with me. How many groups we have?
So you have two groups.
You have two groups. Which one? This one?
You have that one and that one. The other
The
one does
horizontal.
horizontal. Yeah.
So basically, you know, my function is going to be 1, 2, right? Let's go ahead and do it with the same thing we did, right? Group 1 is just horizontal, right? So in that case, you know, I go ahead and just do it like this, right? And this is looking to what? To the x, not the complement of it, right? So basically, here's
So
x.
it's just going to be x.
And then, you know, let's look at the group, the other group. The other group is basically vertical, right? So let's go in a vertical. So it's going to be like this, right? So it's actually looking to what? Y.
Yeah.
Much better than, you know, postulates, right?
Professor,
Yes.
is it possible to have a group of 1?
Yes. You know when? Like this. I have to make a group 1, right?
Okay, but I mean in the same in the case we have above, right? Is it possible to just like, let's say
And
like
it's going to be optimized.
you have to optimize?
Yeah, this is the best optimization. You know, what is the target of KMAP from your point of view? Optimization.
Yes.
When I say optimization, it has to be ultimate optimization, right?
Okay, just a random question. Let's say what you did for group 1, right?
Mhm.
Taking the one on the upper right and on the lower right.
Like this?
Yes.
Okay.
And then imagine for group 2, you just took just 1. You didn't group it into 2. Would it give you the same thing if after writing the equation you break it down, you try to optimize it?
Then you have to make an optimization, exactly. But then, you know, that doesn't mean that you optimize KMAP, right?
Yes. Okay. Yeah.
Okay, thank you. So is it clear to everybody what I'm doing or not?
Yeah.
Yep.
Yes.
I think it's a piece of cake. It's just a matter of what practicing, right?
Yeah.
So now, is the two variables KMAP, it's something famous? I don't think so. You know what I mean? You can still do it by hand. You don't need even KMAP, right? Maybe 8 states, it makes sense, right? 16 states, which is 4 variables, it makes more sense to me because, you know, mistakes can happen. Like for instance, when I made the XOR thing in front of you, right? You kind of like, you know, you got in the middle of like, you know, how did you make it, right? So one of the things I like to do in front of you before I go into the higher level, then I can back to the point of the full error, is telling you there is shapes of ones in a table can give you an estimation what logic this table is talking about. What does it mean? So do you remember, for instance, this particular one, right? This particular one, we said this is 0, 1, 0, 1. It's up to you. You can write it or you can just imagine in your brain. That's fine. Anyway, so we said this is a group by itself. This is a group by itself due to what? Due to there is no neighbors in the weather that's, you know, going to be horizontal, vertical, right? You guys agree? This, from your point of view, look like what? Do you guys play chess?
Yes.
So it looked like what?
Pawns, I guess.
Do you
Everyone
remember
see each other?
yeah? Do you remember the chess mate, the mate of the chess? It's the different colors. So such a kind of thing, it can be for me as a designer, obviously saying this X XORed Y. So when I see such a kind of thing in front of me in the table, I have to have indication those two variables are XOR. That's why the K-map look like that. Okay, sounds good.
So it's like a memorization, or like you just spot it.
Yeah, I mean, because if I don't want to memorize it, let's break it, right? This is group 1, this is group 2. Do you agree? So fxy is group 1 ORed with group 2. Do you agree? Now, if I look into the horizontal vertical for each group, so this actually X complement with Y. So here is basically X complement Y, or with the second group, if I horizontal and verticalized, so gonna be here X with Y complement, right? So gonna be here X with Y complement. What is this from your point of view?
XOR.
XOR. Make sense? So that's why if you see such a kind of like a checkmate thing, then chess mat, then you just go ahead, or checkboard they call, then you just go ahead and you will call it XOR. That makes sense? But if you see it like this, what does it mean? Huh?
Still XOR?
No. It's gonna be the invert of it.
Oh,
X
NOR?
NOR. Let's see whether that is correct or not, right? Pretty much, if I look at this, those are the one I have for this. And if I look at this, those are the one I have for this. So this table is basically X complement, Y complement, X, Y. So this is an XOR. And everybody know XOR followed by NOT gate is XOR. That makes sense? That's from the last lecture. So it depends on where is the one distributed in on the map, right? So the map in front of me in this case is actually XOR, while the map in front of me here is an XNOR. This is for the 2 variable K map. Sounds good? Hello.
Yep.
Okay.
Yep.
Now we already killed 2 variables, right? There is one I can actually add into it, which very interesting. So, the digits we have in a binary can hold 4 different type of values. People will come and say, how? You just told us 0 and 1. But I can tell you something else. In the computer, the data type of digit can be 1, can be 0, it can be Z, it can be X. What is X and Z? So X, that means I don't care. In this particular state, I don't care what will be the output. Then that's called X. If the input is not connected at all, then they call it high impedance, Z. That means there is nothing connected. There is no current even moving in the wire. So they call it Z. For the digital logic, we don't care about this. We just care about X. So pretty much, frankly speaking, we can have 1, 0, X. 1, 0, X. So how can we apply this in the truth table? Do you guys agree? So maybe I have a truth table here of A and B, and the output is called S. So how many states I have in this table from your point of view?
4.
4. So here is 0, 1, 0, 1, 0, 0, 1, 1, M0, M1, M2, M3, right? So imagine this table is covered as follows. So basically here is 1, X, 0, X. Okay? That's basically my table. So if I want to do a K-map here, and instead of going in the postulates and giving myself a lot of time to think about how can I optimize it, so this is covered by 2 variables input K-map, right? So in that case here, 1, 2, and here, right? So in A, B, 0, 1, 0, 1, and this is M0, M1, M2, M3. You guys agree?
Yep.
Let's place the S inside the K-map based on the location. So M0 is 1, M1 is X, M2 is 0, M3 is X. So in that particular case, K-map is very, very tricky. Why? It says if the X getting close to any of the one group, it can compensate it and group it. What does it mean? So this one, if I keep it 1 like this by itself, it will cost me to have an AND gate between A complement and B complement, right? So basically what K-map reduction mathematics way said, you know, assume if here is 1, then I can group it like this. Then it actually helped me to reduce gates. Then, you know, it will just talk about A complement. Then somebody else will tell me, what about this X? This X is not actually helpful anymore, so I can just put it with 0. Again, so if you have a group and you found out this group is like, you know, let's say I have like, you know, let's make another example. Let's have this table like this, right? 1, 1, 1, X. Y, X, 0, 1, 0, 1, right? So if I consider X here 0, how many groups this table will cover from your point of view?
All 4?
No, basically I'm talking about group, not terms. Terms you are 4, you're right. But you know, group, you already have group and group, right? So 2 groups, right? But magically, if this X turned to be 1, how many groups I'm gonna have? I will just have 1 big group.
Yeah, 1.
So did you see what I'm doing now? I'm using as a designer X, it depends on my what? My desire here. So basically I see that X is helping me to reduce number of gates based on the reducing the groups to be 1 group. Then I can use it. If not, I just excluded 0. So in this case, I use this one, but this one I put it 0. But here I use this one because it will make it 1 group and finish it for me instead of tiring myself with 2 groups and having a bunch of AND and OR gates. That makes sense?
Yep.
Okay, so we're gonna practice a lot. The whole chapter is K-map, so we're gonna practice a lot. So at least, you know, I want you to understand what does X mean? How did we place X in the 2 variable K-map, and how can we play in the K-map 2 var? Now I'm gonna move my gear into the 3 var, which is more realistic. There is a wide range of application actually using the 3 var. So 3 var K-map, var variables basically. So how it works, we said how many states we have if we have 3 input variables.
8.
8, correct. So 8, so I can make 8 here. So this table or this map in front of you is representing 8 states coming out of what? 3 variables. So what is the 3 variables? As I can see, I can put here X, Y, Z. Why I'm ordering them like that? Because, you know, my table placed like this, X, Y, Z. Don't write it Z, Y, X. Don't go like this. You have to go from the left to the right like that. Why? Because if you go the reverse, you're gonna use something that's called orthogonal K-map. again, when you are taking the truth table, placing it in the K-map, you go from the left to the right based on the variable's location. So in that case, X here, Y and Z will be there. Let's clear up the rest. Okay, sounds good. Now we're gonna start placing the numbers on it, right? So here is gonna be 0, 1. X can be 0, can be 1. You guys agree? Now there's a little bit trick you need to memorize. So YZ, it's basically can bring me 4 states, right? So we're gonna be 0, 0, 0, 1, Somebody will tell me 1, 0, and 1, 1, right? This is not accepted in the K-map. The K-map, the last 2 will be flipped. The last 2 will be flipped. What does it mean? That means this will be here, this will be there. Again, so 0, 1, here, 0, 0, 0, 1, and then this will be what? 1, 1, 1, 0. We're gonna appreciate this in the optimization, and I can give you the reason later, but at least you need to remember that. Now, let's put which state what. So here, basically, M0. Why? Because X0, 0, 0 is M0, right? Then, 0, 0, 1, M1. Then here, 0, 1, 1 is M3. Then, 0, 1, 0 is M2. Here's what? M4, M5. 1, 1, 1, M7. Here's 1, 1, 1, 1, 0, M6. Sounds good? So far, so good?
Yeah.
I'm gonna make this full adder thing in front of you, and then later, next, in Wednesday, we're gonna practice more possibilities on the table, so I can tell you how did I optimize it. Really, really fun, So if you remember, the X, Y, Z produced to me sum and carry out. Do you remember that? And that table was 8 state, right? 1, 2, 3, 4, 5, 6, 7, 8. So 0, 1, 0, 1, 0, 1, 0, 1, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. M0, M1, M2, M3, M4, M5, M6, M0. Remember the adding, so gonna be here 0, 0, here 1, 0, here is 1, 0, here is 0, 1, here is 1, 0, here is 0, 1, here is 1, gonna be 0, 1, here is 1, 1. So let's get this point, right? I have M outputs coming from this table, so I'm expecting to have M K-maps. So every single output, it has its own K-map, right? So I can, based on this anatomy, I look that, I have S and C out. So pretty much I know that I have 2 K-maps, one for reducing KS and one for reducing C out. Let's go in the S, so I can show you how it didn't end up with. So M1 is 1, right? M2 is 1. M4 is 1. M6 is 1, I believe. No. M7 is 1. This one remind you is what?
Sorry, which one?
The table. When I draw in front of you zeros and 1 inside the table. It does look like what?
4.
It's not a
Oh, it looks like an
what?
XOR.
Yes, because it's chess. The chess thing. Look, do you remember the chess thing that I made in front of you?
Yeah, XOR.
Yeah, this is XNOR here. Right? But you extended, right? So look at there. So that's actually basically X XOR Y XOR Z. Now you figure out why I make it A XOR B XOR C?
Oh.
Okay, now we need the K-map for the C out, right? So I'm gonna draw it again fast. So gonna be 1, 2, 3. So gonna be here X, Y, Z. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Here's 0, 1, 3, 2, 4, 5, 7, 6, right? So here, M3 is 1, M5 is 1, M6 is 1, M7 is 1. If I look to this, how many group I can have from your point of view, from whatever we learned before, from the two variable, how many group in this can be taken? Somebody can tell me. Give me an estimation from your point of view.
Would it be 3?
3, you're right. Why? Because, here, group 1. Then, I'm looking for this to be group 2. I'm looking for that to be what? Group 3. So now I cover all of them, right? So pretty much the C out as a function of X, Y, Z is equivalent to group 1 ORed with group 2, group 3. So now I can start getting whatever I learn out of it. So here I look at horizontal, vertical. Basically, the efficient here is going to be the, it's going to be what? It's going to be the vertical, and then, sorry, the horizontal here is X. Then I look to the vertical of it. So the vertical of it, this case, because it's already 3 var. So I look in here. So that's really cool. I see which one is similar and I take which one is not similar. It will be 1. So in this case, I'm looking for what? This and this are similar. So that means Z.
Sorry, what's similar?
Sorry, how did you get X?
Again, this is 0, 1, right? And this is 1, 1.
Okay, sorry. Let's start with the X first.
Yeah,
Sorry, I
let's
think
look at X,
Kush needs
yes.
to. Yeah.
Here's X, right? X is equal what?
Oh, I thought we were doing the vertical first. Okay, okay.
Okay, so now it's X. Now, after that, I'm looking for the vertical part. So vertical part, I'm looking to this and this, right? Those guys is pointing to this one, right? This one and this one is Z. Y is here is Y complement and here is Y, right? Y and Y complement 1. So that's why I'm taking this one and this one together to be Z.
Oh, okay. Yeah, okay. I got it. So the 0, 1 is X, Y, Z in the one.
Exactly.
Okay.
Because you remember many terms. So basically you group them, right? Anyway, now let's look to the group 2, right? Where's group 2? So let me have a different color. So group 2 is this guy, right? No, I made group 2 already. I need group 1. I'm sorry. Group 1 here, right? So in the group 1, I'm looking horizontal and vertical, right? So horizontal, vertical. Let me give a color. Vertical like this, right? Oh, perfect. I see there's solo here, Y and Z, right? Y and Z. But if I go horizontal, it's going to be X with its own complement. It will go away. So that's why I have this term. Let's go into the third one. So the third one, it will be this, right? So I go this way to be what? X. And then, I go this way and this way. So I notice here, this is 1 and it turned to be 0. So that means Z is out. But this is 1 and this is 1. So that means it's going to be Y. Does look similar to whatever I give it to you in the beginning? Hello?
Yes.
Yes.
So now you understood how I made the optimization?
Yes.
Yes.
Okay. It's 2:13, so you have 2 minutes just to take some rest before you will move to the next class, right? So
Yes,
if
I'm
you have
just
any-
absorbing it.
yes.
Can we?
I promise you it's really fun. Go ahead, sir.
Can you scroll up for the first one, the sum one, real quick? No, the sum one.
The first one, right? In the beginning.
No. The your 3 var
First-
K map for the first
part.
one, the sum one.
Here.
This one, yeah. Okay. So that one is X or with Y.
By the way, I put the recorded video. You know, guys, I put it under the blackboard, right?
Yes.
So, please
so
watch it as
here-
well. Yeah.
So here it's XORed with Y because the only ones that have zeros on them are the Y's, right? And the 0 and 1 cancels out.
Oh, basically, you see that? Do you remember this?
Yeah.
Where is it? It went somewhere in the first dimension. I had it somewhere. Here.
But
That
you
make
have
it
Y
what?
and Z.
That make it chessmate.
Yeah.
Yeah. Now,
But
if
you
you
have
extend
Y
it,
and Z though.
huh?
You have Y and Z though. This one's just X and Y.
Yeah, I
So if you
understand.
s-
But if you extend it, it can be
Mhm.
X, Y, and Z, right?
Mm-hmm.
You understand what I'm saying?
Yeah.
Here, extendable, because this table is now covering X, Y, and Z. So the
Yeah,
same
so-
behavior, X, Y, and Z.
So if you have the fourth
And it's gonna be all
variable
of them
K-map.
XOR to each other. Yes.
Okay.
I'm gonna show it to you when I will talk about the 4.
Yeah. Okay. Yeah. It's baby steps. Baby steps.
Yes. They're even more fun. We haven't seen the more fun, yet. But
I can see
now it's a little bit fun.
I can see why you can't go up to 6. Okay. Happy pain.
And now it makes sense.
I'm trying to do the 2 variable and yeah, I'm just trying to figure it out right now.
What do you mean?
Well, if you do the truth table for n, it'll be 0, 1, 1, 1, right? The K-map?
You mean this one?
No, I'm doing it. I'm just doing something on the side right now. I'm just trying to figure out, play with and I'm making it. Yeah,
Okay.
I'm just trying to make it and right now.
Anyway, can you do me a favor, guys? Practice, because we're getting close to the first midterm, right?
When is our first midterm?
Check the syllabus. I think it was.
It says the 10th.
10th.
How does that happen,
Oh, next month.
Professor? Do we take the midterm during class or is it on Blackboard?
No, the day you're gonna have midterm, you're gonna have the whole day.
Oh, okay. Thank you.
So basically, my philosophy. You guys at home, right?
Yeah.
Internet can be dropped anytime, right? So
Right.
I don't give you a class. What I can do, I can just tell you the whole entire day till midnight. You have the time to submit on the grid scope. Before
Okay.
the day before the first midterm, I will give you a whole entire story about how can you submit and how gonna work and everything.
Okay.
Oh,
Yes.
how many questions do you think?
It's just giving me anxiety right now.
Yeah, since it's the whole day,
It's just-
The whole day,
It's-
okay, maybe 100, 120.
Okay.
Oh, jeez.
Anyway, it's past the time. You guys have another lectures. I don't want to interrupt you. So please do your best.
The class
Please, promise
started
me
off.
to work.
The class started off great. Now you're just giving me anxiety at the end of the class.
Anxiety of what? My questions are already. Ask anybody else have been taking this course with me. It's really a piece of cake.
Easy peasy, lemon squeezy, right?
It is. And this is my famous statement. It's easy, busy, lemon squeezy. Digital logic. This is the core of the computer engineer. Okay.
All right,
So
thank
anyway,
you so much. Have a
Thank
good
you,
one.
guys. It was my pleasure to talk to you. Please, practice. Remember the homework. You remember the homework? What was it? There was a homework here somewhere in the first dimension. This one. And you made the postulate thing, right? And that due on Wednesday. Also, please do your best and watch the video over and over and over. If you have anything is not clear, and if it's not really clear, just come to me, in the office hours. I'm more than happy to assist you. Okay, Duke?
Okie dokie.
Thank you, guys. God bless you. Stay safe. Thank you.
You too. Thank you, sir.
Great. Thank you, Professor.
Thank you.
Thank you, Professor.